get moving. Okay, I think this is where we left off last time. I think we had talked through the Scotch Marine type of fire tube boiler. This page or this slide is on water tube boilers, and we can see that because the steam is generated inside these small diameter tubes, it can withstand much higher pressures. And so utility industry generates steam. There are such things as supercritical plants that approach 4,500 pounds per square inch of pressure. So if you're going to generate, if you need steam above about 300, you can't use a fire tube boiler. You won't find them rated for that. So any higher pressure boiler is going to be water tube. Water tube boilers, huge size range. Cumberland, TVA Cumberland plant has got supercritical boilers in excess of 10 million pounds an hour. Driving, I think those are 1,300 megawatt generating units. So they can be quite large. We can do saturated. Most of them probably do some degree of superheating. And certainly if you're going to have superheated steam, you can't do that with a fire tube. So that would put you into water tube boilers. Any of significant size are constructed on site. You know, the different components are trucked in and then put together, whereas the fire tube are usually assembled in a plant, set on the back of a big truck and brought in. And there are lots of different styles of water tube boilers. You look at the diagram, we have two drums typically, an upper drum, which is termed the main steam drum. That there's a water level in that drum, and it feeds the steam generating tubes. So there's a mixture of water and steam in those tubes. The steam rises back to the main drum where it's separated. There's devices called steam separators inside the drum. And then that steam may go on for superheating and then on out to the steam system. Lower drum also would contain some water, and also it's called a mud drum because any type solid crud, anything, corrosion products that might fall off the wall will settle to the bottom of the bottom drum. So that's where it gets its name. The furnace is lined with tubes, steam generating tubes called water wall tubes. Burners are either sidewall or in the corners. Corner burners are called tangential firing. And then of course, if they're in the wall, it's just wall burners. And exhaust gases go into atmosphere. That's probably a little better picture. We can see we've got wall burners. We're showing 6 burners over here. These are the water wall tubes that line all of this. There's the main steam drum, and there's the mud drum. Most of these are steam generating tubes, maybe a few superheater tubes in the gas pass as well. A cross section, you get some kind of an idea over here. Wind box, fans pressurize the wind box. It provides air to the burners and for combustion. That's pretty much it. You can see there's a little guy standing down here. This is a pretty good size boiler. Some are a whole lot bigger than this, and some are a whole lot smaller too. Just depends. Okay, let's talk about some common fuels. This is what we typically think about as boiler fuel. We've got natural gas, and then the sales unit is 10 to the third or 1,000 standard cubic feet. And the nominal energy content of natural gas, 1 cubic foot is nominally a 1,000 BTUs. So 1,000 standard cubic foot is 1,000,000 BTUs. We typically, in US, we will compare fuels on the price of dollars per million BTUs of energy in the fuel. We also, when we rate fuels, we see up here in this column, we have this HHV. Anybody know what HHV stands for? That's higher heating value. There's also a rating called lower heating value. And guess what? The higher one's bigger than the lower one. The question is why? Okay, so here's the story on HHV and LHV. When you determine the energy content of a fuel sample, you burn it in a calorimeter. A lot of them, these little kind of spherical devices, they'll load it up with sort of air and fuel, and they set it off with a spark plug or something and burn it, and they immerse it in a water bath. And they let it come to equilibrium, they insulate it, then they measure how much the water bath and the steel and all that increased in temperature. And then they calculate how much energy was released in that process. So you get, you know, BTUs or kilojoules or whatever per kilogram or per pound mass of fuel. Well, so if you have any hydrogen in the fuel, hydrogen is going to burn to what? What's hydrogen burn to? Water vapor, okay? So the question on LHV and HHV is, what is the state of the water at the end of the test? If the water, the H2O created, is still in the vapor state, it contains a lot of energy and it hasn't been allowed to condense, okay? So that energy that gets into the water that gets measured for the fuel is a lower quantity than if the water condenses to the liquid state. So if when we conduct the test, the water that's created from the combustion of hydrogen condenses, it gives off its energy and it's attributed to the fuel. So you would get a higher heating value. If on the other hand, at the end of the test, the water remains in the vapor state, it still contains that energy, and so the energy that is attributed to the fuel is lower. And that's the difference between lower and higher heating values on fuels. So it's common in the United States to rate fuels on higher heating value. In Europe and Japan, it's common to rate fuels on lower heating value. And so you'll see this makes a difference in things like boiler efficiency calculations. If you calculate a boiler efficiency based on higher heating value, you get one number. If you calculate it based on lower heating value, you get a higher number, makes the boiler look better, but the operation is identically the same. So if you're going to compare boiler efficiencies, say big multinational corporations that have plants in Japan, China, Europe, and the US, if their people report boiler efficiencies on different basis, then somebody's going to look good and somebody's going to look bad, and the operation may be identically the same. So you have to be careful with what you're going to report, and when you purchase fuels, or what do you purchase, you know, the specs that you use to buy fuels. You know, you gotta know which one of these that you're dealing with. Okay. We'll talk more about this as we get into some of the combustion issues on the boilers. Number two, fuel oil, is diesel. That's like diesel fuel, except it doesn't have additives. If you buy it at the pump, they put it in a truck, it's got a bunch of additives in there that a boiler doesn't need. So, but the fuel is basically the same, minus the additives. And you see some prices. You see on the natural gas. These slides were put together a number of years ago, and I've never really updated the prices. It says $7 for 1,000 standard cubic feet of gas, which is a million. So that's $7 a million. And you notice we also can do BTUs per pound. And for a gaseous fuel, that would be at standard conditions, standard temperature and pressure. Because the amount of energy you're going to get is going to be dependent. If you compress the gas, then you get more molecules, you get more energy. So it has to be at standard conditions. Number two, the diesel, $1.80. What's happened, natural gas is now much cheaper, and I think diesel probably costs more, somewhat more. The last couple of plants that we were in, we're paying probably between $3 and $3.50 a million for natural gas. So you see the price has fallen in half from when this slide was put together. And that's caused by fracking, hydraulic fracturing, which we've mentioned in here before. Okay, let's see, number two, the sales unit is a gallon. And so that's roughly $1.80 to $2.25, whatever it's going for now per gallon. BTUs per pound, 19,400. And you see that at least in this slide, the fuel oil, the number two, is almost $13 a million BTUs. And I would say that's probably at least that today, whereas the price of natural gas is probably between $3 and $3.50 a million. So if you've got a big boiler, you don't want to be burning any more oil than you have to if you can burn natural gas. It's pretty obvious. Okay, what's number six? Anybody ever encounter heavy fuel oil? Number six is heavy oil. It's very thick, viscous. You can't even pump it very well unless you heat it up. Typically that oil is kept at 160 to 180 degrees to make it pumpable, where it will pump readily. And you can spray it out into a burner and combust it. And of course, the more obnoxious the fuel is, the cheaper it is. So you see here, it's listed as $1.20 or $1. LS is low sulfur. If it has low sulfur content, it's worth a little bit more. If it has higher sulfur content, then it's worth a little bit less because you've got to worry about cleaning up the sulfur dioxide emissions. Sulfur dioxide, in chemistry class, did y'all make rotten egg gas? Yeah, that's a common experiment in high school chemistry classes. It stinks, but that's sulfur dioxide. It is a pollutant. It's heavily regulated by the EPA. And so, if you're burning number six, you can get cheaper fuel for the high sulfur, but you're going to have to then be able to control the emissions. Eastern coal, that's typically bituminous. The sales price here says $45. Yeah, I think it's gone up significantly from there. It also depends on the sulfur content. Some coals have a lot of sulfur. So if you own a coal mine and you're blessed with low sulfur coal, then your coal's worth a lot more. I think last time, when Tech went off of coal about 3 years ago, I think Tech was paying $120 because they didn't have any sulfur cleanup. They didn't have any gas cleanup down there. And so they had to limit the sulfur emissions by, if you don't put it in, it doesn't come out. So they would pay $120 a ton to get low sulfur coal so they could meet their sulfur emissions requirements. Western coal can be bituminous or anthracite. It doesn't have quite the energy. You see the BTU content per pound. Eastern coal, 13, 7, 10, someplace between, you know, and it varies seam by seam. It could be 12, 12.5, 13, 14,000 BTUs per pound. Western coal is typically lower, has less hydrogen, more carbon, which lowers the energy density a little bit. And green wood, 5250 BTUs per pound. It's cheap. That green wood is roughly 50% moisture. It's hard to burn. And it, you'll see a fairly low boiler efficiency because a lot of the energy that you're putting in, you're just evaporating that water that's already in the wood. And the water vapor typically goes up the stack as a gas. And that water vapor takes a lot of energy with it that you can't transfer to make steam. So those are typical type numbers. Let me do one other thing here real quick. I'm just going to talk through this because I write on the board. It doesn't really get recorded. But if you have a calculator or piece of paper and pencil, write this down. We want to calculate the cost per million on electricity. Okay, the cost per million BTUs on electricity. Okay, so here's how you do that. The conversion factor we need is 3412. There's 3412 BTUs in a kilowatt hour, or BTUs per hour in a kW, wherever you want to put the hour unit. I'm sorry? 3412, 3,412 BTUs in a kilowatt hour. So to convert, if I take a million, just put 10 to the 6th in my calculator and divide it by 3412, I get 293. And then multiply that by the cost per kilowatt hour. Let's say we had 10 cents. We're paying on average 10 cents a kilowatt hour times 0.1. That conversion is $29.31. $29. That's pretty expensive compared. I can buy natural gas for $3.50 a million, and the electricity is almost $30. It's like 8 or 9 times more expensive. So do you think you're going to see a lot of people converting natural gas boilers to electric boilers? I don't think so. It's going to, I mean, your cost of operation is going to go up by a factor of 5, 6, 7, 8 just to provide the energy input to make the steam. Now, the electric boiler could be virtually 99, 98, 99% efficient. The natural gas boiler might be 82% efficient. Okay, so assume the electric boiler is 100% efficient. So then the fuel cost is still at 10 cents a kilowatt hour, is still $29.31. If I had $3.50 gas and I had an 82% efficient, just take 350 divide by 0.82. By 0.82. And so that makes it 427. Well, I changed it a little, but not much. I'd way rather pay 427 per million than almost $30 a million. Store 3, that ratio, 6.9. Electricity under that scenario would be almost 7 times more expensive than natural gas. Just a second, I can't. Oh, yeah. Oh, yeah. I mean, a big plant, well, like that flooring plant, they're spending, I don't know, $1.5 million a year on natural gas. So if they converted all of that to an electric source, it would be times 7. Yeah. See, you know, I mean, I always like to kind of occasionally brush on the political aspects of this, but you know, if you're a supporter of manufacturing in this country and you want to ban fracking and the hydrocarbon fuel industry, you're going to put those guys out of business. I mean, they can't make it because you go to other parts of the world, they're sucking up that natural gas or whatever the cheapest fuel source is every day. And yeah, is that bad for the environment? Maybe it is. But when you graduate, Spencer, do you want to have a job? Do you want to go to China to work? Probably not. Well, you know, I mean, there are practical realities to all this stuff you hear this stuff get bantered around in the press all of the time. Have you heard that California is having rolling blackouts? You know, they've got a heat wave in California. You should, for your own education, you should Google this. Northern California is having rolling blackouts because they have basically outlawed almost all fossil fuel generation of power. And now they can't make enough electricity. The winds may not blow. The sun goes down every night. And so now in parts of California, the demand is greater than the supply. And so they say, I'm sorry, Cookville, from 10 o'clock at night until 4 o'clock in the morning, you're not going to have any electricity. Boom. Pull the switch, man. Or, you know, maybe not that long. Maybe it's 2 hours. So we're going to turn off Cookville from 10 till 12. We're going to turn off part of Knoxville from 12 till 2. We're going to turn off the other part of Knoxville from 2 till whatever. And they just rotate it around because the power demand is up here and they can't generate it. And there's not enough transmission lines coming over the mountains to supply it from outside. That's what renewable energy is getting you in California.
My girlfriend's in Central California, and her power was turned off from 2:30 to 4:30 the other week.
Yeah, how long was it off?
About an hour or two.
Yeah. Well, if you Google, I mean, they publish a schedule. So you know when your power is going. So I guess what everybody does, it's hot outside, so you put your thermostat on 60 and you run your house as cold as you can get it because you know you're going to have 2 hours with no air conditioning. So you can get a flywheel effect and get through. And you can't take, you know, once you run the hot water out of your tank, you can't take a hot bath until it comes back on. I mean, I'm sorry, but to me, this is lunacy. I mean, I'm all in favor of the environment and all this other good stuff like everybody else. But at the same time, man, you know what my wife's going to say if our power goes off? Man, she's going to take it out on me. It's not my fault, but I'm going to catch, when she gets in there and wants to take a bath and there's no hot water, I'm going to hear about it. Well, we'll do something. What do you want me to do? Chop a tree down? Have a big kettle like this? And I mean, you know, there, you get in that kettle and I'll build a fire under it, you know? Yeah, we'll get you good and warm. I mean, you know, what are you going to do? Anyway, okay. I'll tell you what, you could not pay me to live in California. Taxes through the roof, wildfires every year. It finally rains and they have mudslides. Income tax, good Lord. I mean, it just goes, I don't know. I don't know why anybody, I mean, it's beautiful to go visit. But God, you can go visit for a week and then get the heck out of there. Traffic? Yeah, after a week, you're ready to go. I agree completely. Anyway, okay. Now that I woke you all up, okay, so let's start getting into, a little bit harder engineering here. Classic boiler efficiency comes from your Thermo 1 class. What's an efficiency? It's the desired output divided by the costly input in the same units, so that the units cancel, multiply it by 100 and get a percent. So for a boiler, what's the desired energy output? Well, it's the steam flow. That's what we want, is the steam. And in energy terms, it's the enthalpy of the steam leaving minus the enthalpy of the feed water coming in. So just enthalpy out, enthalpy in, minus times the mass flow rate of steam. That's the desired energy output from the boiler. That could be, well, that's M dot, so that's a rate of steam. So that's like BTUs per hour or megajoules per minute or BTUs per second, or whatever time base you want. And the energy that cost, the costly energy, well, that's the fuel. That's the electricity, or that's the natural gas, or that's the diesel, or that's the coal, whatever you're buying to burn to produce heat to make the boiler work. Okay? So that's the mass flow rate of fuel times the higher heating value. Now, that could be lower heating value, but like I said, in this country, just by convention, we usually use higher heating value. But if you're going to compare one boiler to the next, it's not fair to use LHV over here and HHV over here. Okay? Because HHV is bigger, so you're going to get a lower efficiency. If you divide by a bigger number, you get a smaller number, So there you go. Okay, so let's look at, we're going to have this example boiler that we're going to kick around for a while in these slides. So we got a boiler that's fired with natural gas, higher heating value, 23,311 BTUs per pound, and that's 1,000 BTUs per standard cubic foot. We're making steam, 400 PSI G, 700 degrees Fahrenheit. I believe that's going to turn out to be superheated steam. So this is probably a water tube. Well, it's 400 PSI G. It's got to be a water tube boiler. Our output is 100,000 pounds per hour, steady. We're going to have this nice plant that's just everything steady and smooth. Not like the real world where things jump around a lot. The rating on the boiler, its maximum continuous output is 120,000 pounds an hour. Feed water is coming in at 600 PSIG, 242 degrees Fahrenheit. Fuel supply, 149,000 standard cubic feet per hour, or 2,480 standard cubic feet per minute. Fuel cost, we're just going to use $10, which is probably at least twice what it would be today. But we see smaller companies, small companies not using much. They may still be $5, $6, $7, $8 a million. Like I said, at home, I'm 8 something, and I'm ticked about it. Nothing I can do about it, but I can still be mad. Okay, so let's determine the operating cost. Okay, so here's some nomenclature. Cap K dot is the cost, the cost per unit time, or the rate of cost of operating the boiler. In this case, we're doing it for a year. V dot is the volume flow rate of fuel. Little k is the cost of fuel, $10 per million or $10 per 1,000 standard cubic feet. And tau is just the number of hours of operation. So 8760. Okay, now 8760 is the number of hours in a year. If I take 365 times 24, I get 8760. How is it you do this? Let me see. So if we take I don't remember how to get the wrong answer now. There's a way to calculate hours per year that you think is right, but it doesn't take the leap year into concern. Does that work for 52? I forget, but anyway, I reviewed some software from Oak Ridge, and they had this number, I don't know, 8724 or something, or 28.
8736.
Okay, okay. So anyway, I had to tell Oak Ridge how many hours were in a year. They just went, oh my gosh. But anyway, you need to know 8760. You need to memorize that number. That's the number of hours in a standard year, 365 days. So you multiply that out, this little boiler is costing $13 million a year to operate. Now that's at $10 a million fuel, so it's far less than that now. It's probably $5-6 million at today's prices. But anyway, just an example. Okay, so let's calculate steam cost. Okay, so well, if it costs $13 million a year to operate the boiler for a year, we get 100,000 pounds per hour times 8760, and they've divided that by 1,000, because notice the units on the cost are per 1,000 pounds. And that extra factor of 1,000 is not shown in the calculation. But that comes out $14.90 per 1,000 pounds. And that's the way steam cost is generally given. You could do per 1 pound, but then you get this obnoxious number like what, 0.0149. So to get a more reasonable number that's more enjoyable to play with, I guess, we multiply it by 1,000. And so in metric units, it might be euros per 1,000 kilograms or something like that. But so, you know, if you go outside the country, you got to be careful, the units will change. But inside the US, this is pretty standard, dollars per 1,000 pounds. And then if you're doing all the calculations, you know, if a big company may have 4, 5, 6 different big manufacturing sites, they can compare their steam cost at these different sites and say, man, these guys are $14.90 and everybody else is $10 or less. What do you got? What's going on? Why is this so high and the rest of them are down here? And then, you know, you can dig into it and try to understand why. Is it a fuel cost, or is it poor efficiency, or, you know, something's going on. That's why these metrics are good. Okay, what kind of efficiency would you expect for a big industrial boiler? Efficiency of, well, it depends on the fuel. Wood, 75% to 82%. Natural gas, I'm sorry, 75%. Natural gas, 82%. And oil and coal, maybe 90%. Huh. Any idea why would natural gas be somehow inherently less efficient than oil or coal when burning in a boiler? Any idea? Yep, louder. I'm sorry. Good try, but no. This is one this one, if you don't know, you're probably not going to think of. It's the amount of hydrogen, it's the carbon to hydrogen ratio. Now, why would that matter? Because the carbon burns to CO2, and the CO2, when it leaves, doesn't carry a lot of energy with it. But the hydrogen burns to water vapor. And water vapor carries a tremendous amount of energy with it. And so the green wood is so bad because it's not that it has hydrogen, it just has water in it. And so that water comes in liquid, vaporizes, and all that water vapor goes up the stack. 1,000, not the nominal number. I mean, you know, you can look in the steam tables and get an exact number, but a Swagen number for water is 1,000 BTUs a pound. Every pound of water goes up that stack in vapor is taken on the order of 1,000 BTUs with it. It's a bunch of energy. I don't know what the number is for CO2, but it's far less than that. Water steam is a tremendous transporter of energy. Water has been called God's gift to heat transfer because it's cheap, abundant, and when you vaporize it, you put that energy into steam, steam can carry so much energy out to a process, okay? So the difference here is wood comes in wet. When you burn it, creates a lot of water vapor, goes up the stack. Natural gas is, what's the chemical? Methane. It's mostly methane. CH4, 1 carbon, 4 hydrogens. And then the oil, like coal has a large portion of its energies in carbon, doesn't have anything to do with hydrogen. And if you look at oil, it's more heavily carbon-based than hydrogen-based, and so you get better efficiencies out of it. So it's the amount of moisture. Okay, let's see. For the example boiler, determine the steam generating efficiency. Okay, this is called the boiler efficiency, first law, whatever, different names. Okay, so here's steam properties. We didn't even make you go look them up. We gave them to you. Okay, so the 2 enthalpies we need in that classic example are the boiler, the steam exit condition from the boiler outlet. We're saying 1361.88, and then the feed pump exit is at 242 Fahrenheit, pressure 600 psi-G. Notice psi-A. Let's knock this home. In the steam tables, you look at pressure. psi-A, absolute. You look at a gauge on the side of a boiler, it reads 400. You don't go to the steam table at 400, you got to add atmospheric pressure to it. Okay? Don't ever forget, steam tables, absolute. You read a gauge out there in the field, you're not reading absolute, you're reading gauge, you got to add atmospheric pressure to it. That's why on that boiler outlet, we got 414.7. We're saying atmospheric pressure, standard atmospheric pressure is 14.7. We got 400 on the gauge, add them together, 414.7. You got to go out to the steam tables. So either you got software or you get to interpolate your little bottom off. Sorry, get some software is my advice. So anyway, you evaluate your enthalpies. And there you go, plug it in. So the equation's at the top. We've already talked through that. 100,000 pounds an hour times the enthalpy difference divided by 149,000 times the energy content of a standard cubic foot. Or you can do it on mass flow of the fuel. You simply have to have the density or the specific volume. So you say the density of the natural gas is 0.043 pounds mass per standard cubic foot. So if you like that, you can do the bottom calculation. Either way, you get 77.1%. Yeah, not so good really for natural gas. We said we could expect maybe 82. So maybe this boiler has some problems. And we're going to be the engineers that diagnose the problems as we go through this, okay? This is known as a direct efficiency, okay? We're going to have another approach at boiler efficiency calculation called the indirect or the loss method, which is what really gets used in boiler assessments. I mean, it's possible to do this. The problem is some of these measurements are hard to take accurately. Depending on the type of fuel that you're using, it may be hard to know on a short period of time how much fuel you're putting into your boiler. Believe it or not, TVA at their some of their big coal-fired power plants, they don't, at any one point in time, they don't really know how much coal is going in the boiler. Over the course of a week or a month, they go, yeah, okay, we put 2.5 bunkers worth in this thing. We know a bunker is, 2 million pounds. So over the course of a week, yeah, they got a good idea. They used to have scales that would measure all that stuff out, but the scales quit working a long time ago, and they just took them out. So when the boiler, when they need to make more steam, they dump more coal in. They don't really know how much is going in at any point in time. But again, over the course of a week, the longer the period of time, the more accurately they know, But instantaneously, over the course of an hour, not so much. It's pretty much a guess. Interesting. And of course, if you have gas, now, if you have natural gas and you have a good gas meter, okay, then you can know pretty well, But anyway, for lots of reasons, some people do this if they feel like they have good instrumentation. They will calculate a boiler efficiency from this classical approach. Most people use a loss method. Okay, well, so why is the efficiency not 100%? Well, losses. Certain individual areas where energy is escaping. Well, let's identify some of these losses. Let's see, okay. So there you go. There's some of them. There's a PTC 4.1, I think that's a performance test code that ASME puts out for boilers. It identifies 15 potential boiler losses. And I think I've got a slide or so, or I'll share that with you. The ones on this slide are usually the main ones. And not all boilers have the same losses. Some of them depend on the fuel type and how the thing is set up. But as you look on this diagram, you see the arrow on the left, radiation and convection. Well, guess what? It's hot in that boiler, and some of that energy, the surface of that boiler can be several hundred degrees. If the insulation or refractory is broken down, I've shot 400, 450 degrees on the shell of a boiler before with an infrared camera. Most of the time you can go pat it, but you don't want to go patting 450 degrees. You'll come out with blisters pretty quick, But in general, you're probably going to see a surface temperature of 150 to 200. But that, if it's a big surface area, that's energy that's lost to the boiler room. So, when it's cold outside, all the guys want to go hang out in the boiler room because it's warm. But in the summertime, you can't get them in there because it's 120 degrees because of the boiler losses. So that's one, radiation convection losses. Down at the bottom, we've got bottom ash. So if you're burning a fuel that has ash, wood creates ash, coal, any sort of a solid, heavy sulfur, heavy fuel oil, number 6, fuel oil, actually creates an ash. It has enough particulates in there that come out. So that stuff comes out of the boiler. They have to take it out. It comes out at some temperature. And so that's energy lost from the boiler envelope. Blowdown, we'll talk a lot about blowdown, but that's water that we're draining out of the system to keep the impurity levels under control in the boiler water, to make sure that we don't scale up on the water side of all the heat transfer surfaces. So that's hot water. And now it's possible to recover heat from that, but a lot of places don't do that. They just take it, basically they may cool it off a little bit somehow, maybe put some regular tap water with it to cool it off, throw it all down the sewer. It's gone. Fly ash, if we're burning coal, pulverized coal, we have little bits of ash that come out in the flue gas we have to collect in a bag house or a precipitator. and that stuff has temperature. And so that's a loss from the system. And the biggest one is the loss of the exhaust gases. Okay, we'll talk about combustion and temperature. How well tuned is our boiler, and how well are we pulling the heat out of those hot gases before we put them to the atmosphere. So there are some examples. Here's this indirect efficiency. We'll do this slide in, yeah, we need to quit here in just a second. Boiler efficiency can also be determined in an indirect manner by determining the magnitude of the losses. So we identify all significant losses, and then we go quantify them independently, each one by itself, and then subtract them all. We put them on the same basis. It's the percent, it's the amount of energy lost divided by the total energy input to the boiler. Each one of those is a percent. We subtract them off 100. What's left is the boiler efficiency. And so our primary losses that we'll really get into are shell loss, blowdown loss, and stack loss. And so you see an appropriate equation. But again, I remind you, there are potentially up to 15 losses on a given boiler. Now, I doubt there's many boilers out there that have all 15, but there's plenty of them that have, well, and even these boilers have additional losses that we oftentimes gloss over because the assumption is they're very small in magnitude. And where there may not be anything we can do to correct them or to reduce them. Okay. All right. I'm going to shut it down there. We'll go over the quiz next time and continue with the indirect efficiency and the boiler discussion. You'll be getting a homework pretty soon, so I would download the measure tool and punch around on that a little bit. I don't think you'll have any trouble with it. I hope not. But we'll get a homework probably I don't know, next week sometime. Probably not probably a week from today. I'll get you a homework out to use the measure tool. Hope y'all have a great rest of the day, and I'll see you on Thursday.